Hi everyone, I'm Justin and I'm the main programmer for Hotwired. And today I'll be talking to you about how to have a rock-solid control system. So first of all, let me go over why you need a rock-solid control system. So a control system, first of all, a control system will give you a huge lead in autonomous. The autonomous period is all just by itself, so a control system is fundamental in having a good autonomous program. And when you have a good autonomous program, that just sets you up for an even better teleop program. So in autonomous, you can set yourself up in a good position for teleop. For example, last year we set ourselves up right next to the mountain so that we could easily just go straight from autonomous into teleop scoring. And in autonomous, you can also establish a good lead. For example, in the autonomous period last year, some of the best teams were scoring around 95 points just in autonomous itself. So this can be a huge game changer in some matches if you have a good autonomous. You can easily get the upper hand quickly and maintain that lead. Secondly, a good control system allows for really good teleop scoring as well. When you have a good control system, the robot can automatically do some functions in teleop rather than having the drivers worry about it, and it just improves reliability and speed overall during teleop scoring. And lastly, it just makes the robot more reliable throughout the entire game, autonomous and teleop. So here's just an example of a really good autonomous program that I found online by team 9006 APS Robotics from Massachusetts. If you could play that video, yeah, could you just play it real quick, if you can. There we go. Yeah. So this is a really good example of how a good control system can set you up for a really good lead during autonomous. You can see how the control system is not only scoring the climbers here, but it also hits the beacon after it scores the climbers. And this is all through its really solid control system. So right there you can see it hit the beacon. And then finally, it uses its control system to also climb up the ramp. And this is worth a huge amount of points, and it can be fundamental in your matches, especially during the earlier parts of the season. So let me just go over some general characteristics of control systems. First of all, control systems use lots of logic and lots of loops and if and control statements. So like in the graphic on the right side, you can see just how complex control systems can get. They can be huge branches of ifs and for loops and while loops and all that kind of stuff. Control systems also keep track of many different data values, like variables. You always want to keep track of like motor values or sensor values, like timer functions, stuff like that. Control systems also use many different algorithms. You might have heard of like teams using algorithms in their code. So they do this to keep track of all the different states of their robot to make sure that they know what's going on at all times. And many of these control systems are actually state machines, which are control systems that move through different stages or states as different criteria occur. So then I'm just going to go into some more features of control systems and just give you some advice overall. So you want to make sure that you're always keeping track of all the components of your robot in your control system. You want to make sure that all your motors, servos, sensors, all of them are working properly so that your control system can behave as it should be. But at the same time, you also want to make sure your control system is adaptable. So if some motor fails at any point, the control system will know that and it'll compensate for that and try to move without it. You should also ensure, this is a huge problem that many rookie teams often run into when they're making their programs. You want to make sure that these control systems are running all the time, or at least all the time that it should be. So always make sure they're like in for loops or while loops, because a lot of teams, they'll just have it once in the code, and then it'll like go through that one piece of logic, and then they'll just forget it for the rest of the program. So if you're like looking for some certain sensor value, and then you find it, okay, great. But you also need to keep looking for it so that you make sure that it's always running. And I cannot stress this enough. You need to make sure you use these little things over here. Use these, please. You need to make sure your code is readable with comments everywhere so that whoever's reading the code can easily see what pieces of code do what. So like as you can see here, this person documented their code with comments so they can easily tell what's going on here. Because when you're in a competition between matches, you only have a limited amount of time before you need to go to like a judging session or a practice field or something like that. So you need to make sure your code is readable so you can easily change something or fix an error somewhere, and so that you can just maneuver around the code as easy as possible. And just some more advice for general control systems. You need to make sure that the tolerance of your control system is always under control. Some tasks of control systems, they need a large error range. So like if you're just moving in some general direction, you need to have a large error range to make sure that you're moving in that direction. But at the same time, if you need to make a really precise movement, you need to make sure your error range is small enough so that you'll accomplish that task easily. So like if you're moving to this one specific part of the field, you need to make sure that you're only moving to that field, because if you move somewhere else, it might be completely off. And you also need to make sure that you know when to use your control systems. So like if you're just plowing through blocks or something like that, you don't need to be using a control system because it's just like a brute force task you're just moving through. But at the same time, if you're doing something really precise, like I said earlier, you need to make sure you're using these control systems. And a huge feature that'll give you a really good advantage in the FTC challenges is if you keep your control systems versatile. So for example, when you're in autonomous mode and you're trying to set up your autonomous with your partner, if you both try to start in like this position right here, you're going to have a problem because only one robot can start in that position. So you need to make sure that your autonomous is versatile and you can start like here or here or here. And you can like go up the mountain, or you can score here, or something like that. So for example, last year, we made sure that we had different starting positions for our autonomous, and we also put in some time delays so that we could coordinate with any partner who, if they started like here, we could start in the other position, or something like that. This also applies to TeleOp. So in TeleOp, you should always make sure your TeleOp program is very versatile. So you can program a lot of different button combinations to make sure that you're ready for every situation possible. And you can also make sure that your hardware and software are accessible, and just the build team can easily reach different components whenever they need to. Okay, so this is probably one of the most important parts of this presentation right here. It's just keeping your control systems reliable and running at all times. So a big problem that many teams had last season was keeping their connections in the sockets and making sure there's no disconnects. So as you can see here, these are just normal USB wires. They can come out pretty easily. So when these wires come out, the whole system can just shut down. And this is a problem that we actually ran into a lot last year, where we'd have these little wires here just come out, and then the whole system would just stop working. So you need to make sure to be using zip ties, and you can also use 3D printed parts like these here. You can find a bunch of 3D printed parts online, like on Thingiverse, or even on our Facebook page. If you look there, we shared some parts there. And if you use these parts, you can secure your wires into the sockets to make sure that they don't disconnect in the middle of a match, and that they're always secure so your control system is working at all times. You should also try to make sure that everything's in good condition, and if anything fails, then it's you can make sure that it's redundant. So for example, last year on our battery powers, we had 2 connections for our batteries. So if one of them failed, then we could just go to the other one and it would still work during the match. And you also need to make sure to carry many replacements. This is extremely important for every single team here. Make sure you have replacement parts for your USB cables, for your motors, motor wires, servos, everything. Because when you're in a competition, you never know what could happen. Any part of your robot could break, or you could have some failure. So make sure to carry replacements to make sure that your control systems will always be running. And this is also a huge problem that we ran into last year. As Robin mentioned earlier, electrostatic discharge is one of the hugest problems we had last year. So you can always make sure to tape up areas that might come in contact and cause discharges. As mentioned earlier, like this tape here on the front of our robot. You should also make sure not to overload your wires with servos. So like don't put 6 servos on one controller. Try to distribute your servos around, or just distribute the power usage all around your robot. Also make sure you upgrade the firmware on your controllers so that you can make sure that they're performing at top condition and they're not running on some outdated firmware. And lastly, as Robin mentioned earlier, use anti-static materials wherever possible to make sure that your control system doesn't fail. So now I'm going to get into some applications of control systems that you can use. This is just a list of sensors that you can use in the control systems that we recommend. So this includes the Andy Mark Never Rest motor encoders, and many of the modern robotics sensors, like the integrating gyro, color sensor, and range sensor, as well as limit switches. So for example, like the Honeywell limit switch. However, sensors that we don't recommend, you could use them, but we recommend that you don't, are the Lego NXT Mindstorm sensors, as the modern robotic sensors are much more reliable and easy to use for programming and just for general use. And if you're up for a huge programming challenge, you can also use some commercial off-the-shelf sensors like this here. So like Adafruit or Maxbotics or Polulu sensors. And these sensors allow for more reliability, but they're also harder to use. So if you're up for the challenge, go for it. And just a quick show of hands, who here has used sensors in their robot before? All right, so that looks like a pretty good majority of people. So I'm just going to go through these sections really quickly. This is just how you can use sensors in your control systems for autonomous. So you can use encoders to measure the distance that your robot goes by just constantly checking the encoder value, and once it hits a certain number, that you know that you've traveled that amount of distance. You can also use time for the same purpose, but it's a little less reliable. But if you need to do some brute force tasks, then you can still use time. You can also use these things, which are range sensors, which combines the ultrasonic and optical distance sensors. And you can use these to track the distance from your robot and an obstacle. So once this distance is short enough, you know that you're too close to an obstacle, so you can stop moving. And you can also use color sensors to detect like the white tape on the field. So if you detect the white color on your color sensor, then you can stop the robot. Or you could use something similar. And you can also use a gyro sensor to detect turning on your robot so that you can control the turning and make sure that your turning is accurate rather than just guessing some value to turn with. Okay, so now we're going to get into some more advanced autonomous control systems. So PID control is a really good way to make your control systems precise. PID control is basically monitoring the power level of your motors and then adjusting them according to the error in where you need to go. So I'm not going to go into this because, you know, you can tell this isn't something you want to go into really simply. Just look at that. But basically, it's a really good way to control your motors precisely and make sure that your control system is reliable and going where it needs to be. And also, you can use encoders to check for stalling. So stalling is just basically when you run into an obstacle and you can't move any further. So if you run into an obstacle and you just keep trying to push against it, you could burn out your motors. So to prevent this, you can check your encoder values to make sure that you're still moving forward. So if you're trying to move forward, but you detect that you're not actually moving forward, then you know you're stalling, so you can stop your motors. So now we can get into some teleop control systems as well. So you can use motor encoders for driver presets. So driver presets are basically just buttons you can program for the drivers to use easily. So when they press this button, so the robot will automatically move some part of the robot to a certain position. For example, last year on our robot, we had presets on our arm. So the drivers could just press a button, and then the arm would lift out to a certain position so that they didn't have to worry about lifting the arm out to a certain position. The robot just did it automatically. So you can use encoders for this purpose by tracking the encoder values on these motors, and then when the drivers press the preset button, it'll just move out to the certain predefined value, and once it gets there, it can stop the motor. So then that's a really good way to have a teleop control system to make teleop scoring a lot quicker and efficient. And you can also use limit switches and encoders for safety during teleop, and also as kind of presets as well. So this here is a limit switch. It's basically like if you've used NXT touch sensors before, it's basically just another touch sensor, like this little button here, when it's pressed by this lever here, it basically acts the same way, but it's a lot more reliable and easy to use. So you can use these as well as encoders to make sure that your robot is functioning safely. So for example, on our robot last year, we used limit switches on the top and bottom of our slide, so that if the slide was trying to come down and it had already reached the bottom, the limit switch would tell the robot that it's already at the bottom, so it doesn't have to keep going and burn out the motor. And another example of how we used this kind of system in our robot last year was with the bucket. So as you could see earlier, the bucket is kind of trapped within the robot here. So if you try to move the bucket when it's still inside of the robot, it could damage the hardware component inside. So we use the encoder values to track where the slide is and how extended it is. So once it reaches a certain point, then the bucket can swing out safely without hitting the internal components of the robot. So we just use encoders to track for this. So now we can get into some more specific examples that you don't necessarily have to use, but it can kind of give you a good idea of what you could use in the future. So last year on our bucket, we used something called an inverse kinematics algorithm. So this basically just defines an x and y coordinate. The drivers can define this coordinate using their joysticks. And then the algorithm will automatically calculate the positions that these two servos have to move to in order to get the bucket to a certain position. So this is a kind of algorithm that you can use in your control system, as the drivers just have to specify this coordinate, and then the whole program will just automatically calculate it for you using these servo values. So this is really useful for speeding up your teleop control, and it really helped us in the long run last year when we were still using that design. And then another example of something we've used before is something called a swerve drive. So in past years, we've had a drive system where each wheel is on a servo, so it can turn like this or like this. So it can move like up and down, and then it can also move left and right without ever turning. So this is a really complicated drive system, so it also has to have a complicated control system behind it. So basically what we did was just tracking the joystick values on the driver controllers and then monitoring the values to see where they're trying to move the robot. So if the drivers move it up, the robot will move that direction, and if they move it to the side, the robot will move that way. And so this is just another example of a control system that you could use in the future. And then these are just some more control systems that we found last year from other teams that we really thought were good examples of control systems. So this is from team Masquerade from Florida. So last year, as Robin mentioned earlier, we used kind of latches to grab onto the bottom of the mountain, and this is kind of where we got the inspiration here. Like you can see these two latches on the bar. So these latches could potentially dig into the ground if they kept them down. So what Masquerade did is they used a specific sensor to detect when they got onto the ramp. And once this sensor detected that they were on the ramp, that's only when they put down these latches. And once they got off the ramp, the sensor would detect that, and then it would put the latches up to make sure that it wouldn't dig into the ground and prevent their movement. And another really cool example was one from our friends over at Vulcan Robotics, Team 8375, who were actually our alliance partners at Worlds last year. So they used two optical distance sensors on their collection system. Since there was a rule that you could only have 5 pieces of debris last year, they kept on monitoring their collection system to make sure that they didn't have more than 5 blocks in it. So once the optical distance sensors detected that there were more than 5 blocks, it would immediately reverse this collection that you see here and just start spitting out blocks until they had 5 again. So these two are just really good examples of control systems that you could also use, or something that you could kind of get inspiration from in the future. Okay, so the question was, in our autonomous program where we start in 2 different positions, is that 2 separate programs or is it just one? So we actually just programmed one autonomous program, and before the match, the drivers would be able to select which program they wanted to run, or which sub-program they wanted to run within this program. So like before the match, our driver coach would select either this position or this position on the joypad, and depending on which position he selected, the single program would go through a different branch of logic according to which position he chose. So it's just all one program. I can kind of go in a little more in depth on how we did that autonomous. So we had a bunch of different options for our autonomous. We had a blue alliance or red alliance option, because it's reversed on either side. We had a close to the mountain and far away from the mountain starting position option, so it could start either right next to the mountain or towards the other side of the field. And then we also had a time delay option where the robot would delay a certain amount of time to allow the other robot to come in before it. And then we also had an option where it would back out of the parking zone to allow for another robot to come in. So if you consider that, that's really just a lot of different autonomous programs put into one. So that kind of allows us to be really versatile during competitions. So the question was, did we ever use multitasking during our code? And yeah, that's something that we always do every year. We make sure that we multitask during our program so that we're like checking this while we're moving, or like we're looking for some specific sensor value while we're also dumping the climbers or something like that. So we always make sure that we use tasks to run multiple things at the same time rather than just doing this and then doing the next thing and then doing the next thing. Because this allows for time management, because you can run multiple things at once rather than having to wait for each one after the other. I can count real quick right now. So we used 4 color sensors right here to detect the beacon. We used 4 limit switches on our arm to prevent it from going too far and burning out the motors. And we also used a limit switch on our bucket to let the drivers know when they have 5 items in their bucket. And we used a gyro sensor to autonomously turn the robot. So that's, 10. Question was, when you have more complex sensors, is it just not supported in Android Studio, or how is it harder to program? So with the modern robotic sensors, modern robotics provides the functions for you to use in order to access the sensor values. So for example, if you wanted to use like the modern robotics color sensor, they have a modern robotics color sensor class for you to use already, and you can just get it from modern robotics. But with these other sensors, there's no predefined classes that you can use to get the functions to access the sensor values, so you have to program all of that yourself. This isn't necessarily like a automatic control system necessarily, but it's also part of the sensors that we used. So right over here, we have 5 LEDs on one board here. It's kind of hard to tell when they're not on, but we use these LEDs a lot actually during our matches. So during autonomous, we use these LEDs to signify kind of which options of autonomous we picked. For example, if we picked blue lines, then the blue LED would show up. And if we picked like close to the mountain, then the yellow LED would show up, or something like that. So when you use a system like this, you can make sure that the drivers know what autonomous they picked, and make sure that if they made any mistakes, they can easily tell if they did, and then they can restart the program. And another huge application that we use these LEDs for was during teleop. So like how I mentioned earlier, we have a limit switch to detect when the bucket has 5 items in it. So when this limit switch is triggered, it sets off another LED so that the drivers know that their bucket has 5 items in it. So we've been using this kind of system for all 3 years so far, and we found that it's really helpful for the drivers during their matches so that they don't get confused or anything like that. The question was about the redundant battery loops, so I can go a little more into depth on that. So on our batteries, there's normally just one Anderson power pole connector that plugs into the main power distribution module. But for us, we soldered our batteries so that each of them has 2 connections rather than just one. So we plug both of these connections into the robot. So Gokul can demonstrate right here. You can see that there's an Anderson connector and another connector next to the Anderson connector. So there's 2 leads that go into the battery. And there's also 2 leads that go into the power distribution module. So if one of these wires gets cut, the other one will still be providing power to the robot. And it's this kind of redundancy that we put all around our robot to make sure that everything's functioning properly. So if there's some sort of failure in one side of it, we'll always have another side just to keep it powered. It's not necessarily, I guess, knowing like if the wire is cut or something like that, but if you can use some sort of logic in your program to detect if something isn't working. So for example, in our drive encoder code, we get encoder values from all 4 motors, and then if one of them isn't working, then it'll just return some crazy value that might be like way bigger or way smaller than the rest of them. So to compensate for this, we sort the 4 encoder values according to how big they are. So if one of them's like 0 and the rest are like 4,000, then it'll sort them by 4,000, 4,000, 4,000, and 0. And then we'll pick the second largest value, so it's kind of in the middle. So that way we can compensate for if one of the encoders stops working, then we don't have to worry about it because we're only picking from basically the average values. So it's just this kind of code throughout our robot that makes sure that if something fails, then the program just compensates for that automatically anyways. So the question was, when the program detects that something fails, does it ever give any feedback or something like that? So that's a really good question, and a really good way to use that kind of feedback is by logging any failures that you might find. So Android, the recent Android upgrade has a really handy logging feature that you can use to log values into a log file that it keeps track of during the programs. So if you log any failures that you find, it's really easy to kind of go back and just look through the log file and see what failed. And it's a really good way to fix your robot's hardware and software failures during competitions and even just testing at home. So the question was, can you talk a little more about your built-in software test features? So do you mean like the checks we do to make sure everything's working? Okay, yeah, so this is something that Robin mentioned earlier. We have just a program dedicated to testing every component of the robot. So this program has a bunch of different subprograms within it that just test every single feature. So for example, like there's one subprogram that tests the drive motors by running each motor at a certain power. So then if we see that one motor isn't moving or something like that, then we can see that that motor's connection is bad or the motor is burnt out. And then we also have tests for every single other component, like each servo, each other motor, each sensor. And we run this kind of program during our testing days, our testing meets, and we also run this program during competitions before every match just to make sure that everything's working as it should be. Yeah, so Gokul and Alex can run a quick demonstration of the test program just to kind of show you what kind of processes we go through. So the question was, how many people on our team do we have just doing electronics and coding and software? So I'm the main programmer, and then I also have just a small team of sub-programmers, like 1 or 2 usually every meeting, that I work with just to make sure that the teleop and autonomous code are all running correctly. And then we also have a group of wire management people who solder and just kind of create the wires that we use throughout the robot. So this team is about 2 or 3 people, different people actually. So overall it's about 5 people. But at the same time, we also have a lot of people on our team who want to get a little more into this side of everything, like the coding aspects and the wiring aspects. So next year, we're going to try to introduce as many new people as possible into this field as well. So she asked, how do you make sure that everyone's coding like with each other, because everyone has a different style of coding, and how do you make sure that everyone's kind of working towards the same goal, I guess? So one way that we manage this kind of is we use GitHub as a place to store all of our code and just kind of have branches of our code. So each of our coders has GitHub on their computer to just upload the code to the main branch and just add software changes to the code. So they can make branches to the code, and then we can have different people kind of go through the code and make sure that everything's as it should be and just kind of error check it. And I guess it's kind of hard to explain how we coordinate everyone's different styles. We all just kind of learn from each other, so we kind of pick up each other's styles as we go. Or if someone has some sort of confusion as to what certain parts of the code mean, then we can just get together as a small group, go over any confusions that we might have, and make sure everyone's on the same page. And so they're running a demonstration of our test program right now. So like they can just, do you guys have it ready? Okay, yeah. So this is just a demonstration of like the processes we go through when testing everything and making sure it's all working and up to date. So like they'll run through a couple different tests right now. Yeah, so like this is just testing every single servo on our robot to make sure that it's working correctly. And this is probably one of the most important features of our software in the past couple seasons, because we've had so many situations during the competitions where we've run into some problem in some motor, like the lift's not working or like the bucket's not opening up. So we can always just come back to this program and we can run through everything real quick, and then it's really useful for physically seeing if anything's not working as it should be. And it's saved us countless times in the past. So I definitely recommend making a program similar to this. Just like the autonomous program, the tester program is all one program, one Java file, and it's just you can use the joypads to kind of select which subprogram you want to run. So the question was, what inspired us to make a test program? So there's a couple different inspirations, I guess you could say. So in our very first season, our rookie season, our coaches really drove home how important it is to make sure your robot's always running and it's always running correctly. So the coaches are really, I guess, who we have to thank for this really great program, because they taught us how important just testing everything is. And I guess it also came a little from experience during competitions. A lot of the time we'd be in the middle of a competition and then we'd run into some problem, and especially during our rookie season. So this was always a struggle for us. Like, we'd run into some problem that we just didn't know how to solve. So then after running into enough of these problems, we kind of got fed up and we just thought of ways that we could combat such problems, and then we eventually came to this program that's kind of stuck with us all these years.